जी तो ये this is lecture 2. It's on calculus on subsets of. I'll try to speak slowly because last time I finished too early. So calculus on subsets of Rn and the tangent space. So, you know, a large part of physics is about vector fields, their integral curves, and invariant functions. So at the moment you won't understand what I said because I have not even defined any of these things. So what I'm going to do is I'm going to define all these terms which I just spoke about, right? And you cannot do this without a clear understanding of what a tangent space is. Okay, so so what is a differentiable curve? Okay, so let I be an interval. Actually, for technical reasons, we take it to be an open interval. Let I be an open interval. Okay, a differentiable curve C from I to Rn is a function all of whose components are differentiable. So, is a function C from I to Rn so this is going to have n components, right? We write it x1t, xnt, where each function xi is differentiable. So what's a differentiable function? Tell me. Muneeb? Your name is Muneeb or Mujib? Mujib, yes.
A function whose derivative exists is called a differentiable function.
That's right. But in this course, we for technical reasons, we take it to be you can differentiate it as many times as you like.
Okay.
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 So each xit can be differentiated to any order. Okay, so this is how let me draw a picture for R2. So C will be this is the trace of C. So let me write this. The
So अगर हमारे पास if I have something continuous curve and I draw a tangent. So my assumption is that I can go on drawing the tangents and nothing deters me. So when you say that we assume that it can be differentiated to any order, is there a further restriction or condition that we need to pose to assume that it can be differentiated to any order?
That's an extra condition.
Okay.
Right. I think it'll take too long to explain why they do that. I think basically it's because of partitions of unity. It's a technical thing. You need it for integration theory, and so so the trace of. I mean, I think many things you can do by up to sticking to differentiability up to order 2, because you need to.
Actually, by definition of a manifold, a differentiable manifold, a smooth manifold, any curve on that has to be infinitely differentiable. C infinity, as they call
That's
it.
what.
Yes. And just so that students can relate to the differential geometry lecture, this parameter, this t over here is a parameter. And everybody was very confused. What is this t? He didn't say it is time. When I put S over there, I didn't have to tell you what S is. S is just a number between, in that open interval I. And that xi of t, Professor Azad is calling it I called it mu. So just keep in mind that he's not doing anything that we haven't done as yet.
Yeah, it's the same thing. But maybe you use S because of arc length.
Yeah, this is
Arc length.
But here,
arc length.
because arc length is a natural parameter.
Affine parameter.
Yes, yes.
Yeah.
Yeah, it's a natural parameter. But here T doesn't have to be arc length. T can be just so the interval I, and T doesn't have to be. You can always reparameterize a curve so that, but we don't need it. So the trace of C is by definition all points Ct where T is in your interval I. Okay. So the picture looks like this. So I have some. This is Ct, right? So let's see. Let's see that I have a curve which doesn't go to. This is your interval I from A to B, and for every point T you have a point with two coordinates, in this case xt and yt. Okay. So C prime T is by definition this vector x1 prime T and x and so pictorially here in this picture this so this is called so C prime is called the velocity field along the curve C. Okay. Okay. Now I come to the main point. Let Z be any arbitrary subset. Okay. So, I am trying deliberately not to give the impression that I am going to have a heart attack. Today, I hope I am not giving that impression. Okay. Dr. Vikas tell me, are you okay? I said, yes, but then I listened, yes, I was huffing and panting too much. I don't know why. Okay. So, a differentiable curve C is a curve, a differentiable curve in Z is, by definition, a curve C from I to Rn whose trace is in Z. Okay. So what was the definition of trace? Set of all points Ct where T runs through your interval, and we require that these should not land anywhere but precisely on our subset. Okay. So for all T in I, Ct is not just some arbitrary, but Ct is in Z. Okay. Okay. So
Can I ask why you call it trace? It is just a curve. In physics, we call it curve, and that surface on which it is called a manifold.
No. It's
What's the
no, Parvez. You could have something like this.
Okay, so that manifold then
It's not
intersects.
a manifold. It's a normally these are algebraic sets. They are defined by polynomials. So if you do, this is a dialogue between myself and Parvez. Okay. So so if I take xy is equal to 0. So for me, this is a good old. This is okay because it consists of x-axis and the y-axis.
Yes.
So it's not a manifold technically, but it's defined by some equation. So a generalization of linear algebra is algebraic geometry, where you allow arbitrary polynomial functions, for example.
So what does trace?
Trace, for me, a curve is a function from an interval into Rn. So maybe in geometry you call it a parameterized curve.
Yeah.
Right?
Yeah. Where t is the parameter.
Where t is the parameter.
Yes.
But for me this is definition. Okay.
Okay.
A curve for me is just a function from an interval to I, and what you see is what you think of a curve, right? For example, so x square plus y square is equal to 1 in R2. This is of course a circle, but you could have many different parameterizations. For example, you could have cosine theta and sine theta, or you could have sine theta and x is equal to sine theta, y is equal to cosine theta, things like this, right? Or you could solve for one in terms of the others. Then you would not have parameters. You can fix things so that everything is okay. Is it clear, Parvez?
Well, we would call the set of points x squared plus y squared equals 1 a manifold.
But
Are you okay with that?
Of course.
Good.
But I have not even defined a manifold. It's good for students to see different viewpoints.
Good.
One is what Parvez is showing, and I'm taking a very, pedestrian viewpoint.
No, I was taking the pedestrian.
No. You have in manifold you have to deal with transition functions and all these things, right?
Yeah, but that's transition functions we've dealt with. But is just a set of points on which there's a concept of distance. So it's a metric space.
No, that's a Riemannian manifold.
Riemannian, yes.
For,
We're only interested in Riemannian manifolds in physics.
Mathematicians are not only interested in Riemannian manifolds.
Okay, so you are going beyond physics and good.
Yes.
Good,
This
good.
is the classical approach.
Okay, good. I'm all ears.
So,
yeah.
In mathematics, something which has fixed degrees of freedom, that's called a manifold. What is the degree of freedom and all? That's exact. These charts and so on are exactly this concept of degrees of freedom. Okay. So this part was only between myself and the instructors. Okay. So forget about it. Okay.
So the trace of C here, trace essentially means how to know where I am on a particular trajectory.
At a given time. Yes. Of course, it could come back. Okay. Yeah. Okay. So. Okay. So. What is the tangent space at a point? At a point P of P and Z. Okay. So look at all. So take a curve. This is just the I'm fixing the base point for convenience. Take a curve C from minus epsilon to epsilon into Z, which is differentiable, and at time t equal to 0, C0 is equal to P. Okay. So differentiable, I told you what it means. All the components of C are differentiable, but the image points, the trace lies inside your set Z. Okay. Okay. So the vector C prime 0 is called a tangent vector. I'll show you in pictures in a minute. Okay. So this is called, so the tangent space at P is the vector space generated by, spanned by all tangents at P. Okay, so
I think you mean all curves or all whatever you call them curves. Well, all curves.
you take all curves and you look at the. Yes. You so.
So it's not all tangents, all curves passing.
No. The tangent space is by definition the linear span of all the tangent vectors. So you take, so let me draw a picture. Okay. So, so I think the best is to do, so example. What is of R2? Okay. So this is R2, I fix the basis and I take a point P and I take one curve, right? It will give me a tangent. Let's call this V1. Take another curve. This is, let's say, and the tangent is V2. How do we add them? What's the difference between tangent vectors and ordinary vectors? These are vectors exactly as in physics. These are vectors whose initial point is P. And how do you add vectors? By the parallelogram law of addition. Okay, so you add them vectors at P by the parallelogram law of addition. Okay. Now I'm going to use a notation which I will use only once in this course, just for clarity. So we write. So how do you do this algebraically? Yes, and your question? The C of the. So no, I understood what she was saying. Give me an example of a curve in R2.
Let her repeat the question so that.
Yes, you said what is C of 0?
Follow, no? Otherwise it is not recorded.
Okay.
सर मैं ये कह रही हूँ कि यहाँ पे C of 0 equals to P है ना, what is meant by that? और जो हमने वहाँ पे वो draw
This is what I want to ask you now. Give me an example of a curve. Give me an explicit example.
Sir, y equals to x square is a curve. Is a like
No, y is equal to x square is a curve, but as a parameterized curve, what is it? This is not my definition. Y is equal to x square is the trace, what you are showing to me. Good question. So think about it. Let's think about it. We are in no hurry. Y is equal to x square, right? You say it's a curve. I agree with you 100%. But this is not how I defined it. I defined it to be a function from some interval into R2. So can you think of it? No, this is a very important point. Okay? What is the independent variable here?
x.
So you take x is equal to t, and then y will be equal to t square. So as a curve, this parabola is defined by okay, I don't have to take c of x by c of x is equal to x and x square. Okay, but normally in my mind I am thinking of the I'm thinking of C as something which evolves in time. Yes. So that's why I usually denote the parameter as t.
T.
Right? There's nothing holy about it. You can take it anything you like as long as you understand what it is. Okay? Okay. So now tell me, what will be C of 0?
0 0.
Of course, C of 0. What is C of 1?
1 1.
1 1. Right. So if I want to So give me a point, give me one, let's take point P, 1 and 1, right? Parameterize it around this point so that its value at t equal to 0 is 1. So what would be, so I can take t minus 1, 1 minus t, 1 minus t square. I put ct, okay?
Yes, sir.
And now what is c of 0?
1 1.
It's 1 1.
Yes.
Is it clear now?
Okay.
Okay. So we just fix the base point for our convenience.
Okay, sir. Thank you.
0. So when you want to concentrate on the tangent space at a point, you parameterize curves so that they all pass through that point, right? And if your given parameterization was not such, because if I put 0 0, I only land here. So if I want, so either I have to change the definition that a curve can be is a function from any interval to R2, curve in R2, and then I don't have to look at 0. Okay. So this is just for. So let's get back to. Okay. So we denote a vector V with components A and B by B is equal to P, and then okay, so this shows it is starting from the point P, and you go A units along the x-axis, and where you finish you go B units along the y-axis, depending on whether B is positive or negative. Okay, and you add two such vectors V is equal to P A comma B, and W is equal to P C comma D. The V plus W is, by definition, it should be a vector at P, and what should be its components? A plus C and B plus D. Okay. So from now on I am never going to use this notation. I will just write a vector with components, and it's understood where it is, what is its origin. Okay. So from now on we'll, here for R2, of course you normally would add P plus P, right? But this doesn't make sense. If you are on a circle, you can't add 2 points on a circle, right? Can you? This only in so normally it doesn't lead to any confusion. So from now on we will omit the initial points. As long as we understand what they are. Initial points whenever it is clear from the context, right? Okay. So for P in R2, this is just a copy and if you change your point, how many coordinates for the point? 2 coordinates. And how many for the tangent? 2. So you are moving in a 4-dimensional space, right? You will be moving in R2. Okay. Now the next thing I will write down, but let me first explain to you verbally. I want you to imagine. So you imagine a circle, right? So what are the tangents? So let me show it. Okay. So for every, so here is a point P, and the tangent is this one, right? I'll show it to you in a minute. This position vector and this vector are perpendicular. Okay. So what's the tangent? What we call in mathematics the tangent bundle. It's all the points together with the tangent vectors. Now here you can do something special. If you take the cross product of this with this, what will you get? You will get a vector which is coming out. So what is that? So it will be a cylinder, right? Okay. So the tangent bundle in this case would be because cylinder, which is okay. This is one dimensional and this is also one dimensional. So what's the dimension of a cylinder? You have 2 degrees of freedom, right? So at every point it's a circle. So theta for that, and then you for the location of the point you have 2. Yeah. So okay. So this is a copy of R2. So let's look at some examples. Compute TP of S1. S1 is all the points, so that x square plus y square is equal to 1. Okay. So let P be, so this is how it looks like. I mean, you can take it anywhere, but let's take the standard circle. Okay. So take P any point with coordinates AB. So take a curve C from minus epsilon epsilon into S1. So the components of C are so Ct is equal to xt and yt. Okay. So by the way, why am I doing all this? I mean, it's clear that the tangent space is one dimensional. So why am I doing it? I am doing it because this method will work when you cannot draw things. For example, there is a very famous which will look all the time, SU2. SU2 is nothing but a sphere in 4 variables. Okay, you don't understand it because I have not even defined for you what is SU. Okay, but I am just telling you that why we do this. Okay, so X and Y are not arbitrary. What equation do they satisfy? Remember, it's a curve from this to the circle. Okay, so xt square. So xt square plus yt square is, okay. Differentiate this. What do you get? You always do this when you want to compute tangent space. What do you get? 2 times xt times x prime t plus 2 times yt y prime t. So you get 2 times xt x prime t plus 2 times yt y prime t, and this is equal to 0. Plug in. So at t is equal to 0, you get two times x0. What was x0? Take curve C which passes through with C0 okay. So of course a square plus b square is 1, right? So what do you get? You get 2a times x prime 0 plus 2b times y prime 0. Okay. So C prime 0 is 2a. So C prime 0 is x prime 0 and y prime 0. Okay. Now can a and b be both 0? Of course not, because a square plus b square is 1. So let's suppose that a is not 0. So suppose now a square plus b square is equal to 1. So 1 of a or b say a is not 0. Then I can solve for what? I can solve for x prime. What is x prime 0? X prime 0 is equal to minus b y prime 0. So C prime 0 is this you get this is equal to 0.
So then you divide by it.
Yeah, so I divide by it and what do I get? I get x prime 0 is equal to minus b times y. Oh, I forgot that. Oh, minus b by, sorry, minus b by y prime 0. Okay. So, therefore, C prime 0 is minus b over a y prime 0 okay. So, C prime 0 is contained in the set of all vectors of the form minus b over a u comma u. Okay, u can be any real number. So, what is the dimension of this space? Is it a vector space? If you take two such, you add them, you will get something of the same type, right? So, what is the dimension of this space? It's one dimensional. So, C prime, so T P of S1 is of dimension and how do I show it is exactly of dimension? I have to exhibit a curve, but C itself is a curve, right? So, the dimension of the tangent space is 1, okay. So, to show equal, so dimension of to show equality I have to exhibit a curve which passes through, which is on the circle, and which is a non-zero which is on the circle and passes through with a non-zero tangent. Okay, geometrically, as I told you, it's obvious. The circle itself so what's the normal parameterization of the circle? Cosine theta and sine theta. So I can write A and B as A is equal to cosine theta 0 plus epsilon. So A I can write cosine theta 0 and B as sine theta 0, right? So then what will be my curve? Cosine theta 0 plus t and sine theta 0 plus t. Then at t equal to 0 it will pass there, right? So this is if you have some parameterization. If you don't, still you can do it. So let's do it in a way that will work for a sphere. Okay. So now you can.
I just have a question.
Sure.
You say the reduction of the when I say the reduction of the, you say reduction of the dimensionality. Is it because through one parameter u you can define everything? If I need u and v to specify everything, then it will be
two-dimensional.
Yeah.
That's right. I just needed one parameter. That's why it is one-dimensional, right? but it also has a vector space structure, right? If I take two sides of that, I add, I get something of the same type because b minus a is a common factor. Yes.
सर हम इक्वल टू 1 तो समझ में आ रही है, बट लेस देन 1 डायमेंशंस ऑफ टेंजेंट ऑफ p इज लेस देन 1, वो लाइक किस तरह से हम लेस देन 1 क्यों कह रहे हैं?
Because very good question. So from this equation, you see that the tangent space is a subspace of this space.
यस सर.
This space has dimension
1.
1. What did I tell you last time? Dimension of subspace, can it be more than 1? If I give you a vector space of dimension 3, can the dimension of subspace be so I give you a vector space of dimension 2. Can its subspace have dimension 3?
नो.
Why?
सो बिकॉज वो हमारे पास लीनियरली डिपेंडेंट हो जाती है ना.
बिल्कुल, ये हमने साबित किया था ना.
Yes.
Right. So because the tangent space is a subspace of this, its dimension is, this is one dimensional, so the dimension of the tangent space would be at most,
इक्वल टू और लेस देन.
it would be equal to or less.
ओके.
Right?
यस.
And now I have to prove equality. Geometrically, it's obvious that the tangent space is one dimension. But I want to give you a method which will work not just for the circle, but it will work for sphere and in fact, sphere in any dimension.
Okay.
So although there is a parameterization for sphere in any dimension, we don't have to do that. Just by working with equations, we can get everything.
Okay, sir.
Okay?
Thank you.
So now you can use the parameterization theta goes to cos theta sin theta. Then if AB is equal to cos theta 0, your C of theta, no, C of t cosine of theta 0 plus c and sine of theta 0 plus t. Okay. So what is C of 0? Of course, C of 0 is your given point. Differentiate this, what do you get? C prime t. And cosine of, plug in 0 minus is this a 0 vector? No. Of course not, right? So I produce explicitly for you a curve which has a non-zero tangent, right? Okay. So the dimension of the tangent space would be exactly equal to 1. Okay. So dimension of the tangent space at point P of S1 is 1. Okay. So let us do it by a method which works for, redo this. By a method which works for Sn. This is what will be, this is all points x0, x1, xn so that x0 square plus x1 square plus xn square is equal to 1. Okay. So, from this equation it is clear that we expect the dimension. Parvez, I think Parvez, you did these spheres also in general.
Well, the polar coordinates extended to a dimension.
Okay. So,
I didn't really do it. I said that's
okay,
that can be done.
that can be done. Yeah. Okay.
For instance, if I have two equations,
G.
let's say x1 and x and y, let's say.
Mhm.
So two equations, if I specify one, I can find the other thing, right?
And then you plug in the other one. Yeah. So it should be.
Dimensional n minus 1 are known, the whole system is known.
That's right. That's right.
So geometrically speaking, that is what you mean when you say such a thing, right?
Exactly. There are two ways. One is you go to the theory of manifolds, or you could.
Yeah, I mean to say x square plus y square plus z square is equal to r square, right?
Right.
So if I specify x and y, then z is known,
That's right.
right? So this is what you mean by reduction of dimensionality
No direction, but definition of dimension.
by definition. Yeah. So for a sphere, circle is known, then the
That's
whole
right.
system is known. For a circle, if line is known, then or a point is known, then you can find everything. So there is an equivalent in algebra also.
Yes. Degrees of freedom.
Degrees of freedom. Yeah.
Roughly speaking, all this knowledge, this is to make precise. Do you think Newton and so on bothered about these fine things? No. They had a very good intuition. They were dividing 0 by 0 without even having a proper. All this come later. So what I am explaining to you is in the contemporary language. Yeah. Okay. So
relating it to something which is relating it to something which is known, I think makes it more palatable, I would say.
yes.
Because this is what we do all the time, number of unknowns,
Exactly.
and how you can find. Similarly, in
Yes.
geometry, you have to see that in terms of the reduction of the dimensionality.
G. But the whole problem is that the number of unknowns, I mean, it depends. Locally you can find normally, right? If I take x square plus y square is equal to 1, it's up to you. If x is not 0, then you can solve for x in terms of y, right? And then y becomes the free parameter. And if x is 0, then definitely y has to be non-zero, and then, okay. So exactly. So take a point. Okay. So a square plus b square is equal to 1, right? Okay. Of course, both a and b cannot be 0. Let us suppose a is not 0. Then I can solve for and a is greater than 0. Then what's the solution for a? A is 1 minus b squared to the power of 1 over 2. Okay. So okay. So this gives a parameterization. Curve passing through AB at time 0. phi of t is equal to so b, I put b plus epsilon and then 1 minus b plus epsilon square to the power of 1 over 2, right. So, of course, C of 0 is AB, and why is C oh, I put epsilon, sorry, T. Okay. So, why is C prime T not 0? Look at the second component. What is it? So, even, I mean, of course, I could differentiate this, but it's clear. Look at the second derivative here. It is 1, right? So, C prime is not 0. So, clearly C prime 0, clearly C prime 0 is not 0 because B plus T prime is 1. Okay. So, this shows that the first I showed to you that the dimension of tangent space is at most 1, and now I have exhibited to you a curve with a non-zero tangent. So, dimension of the so I have gone to this great length because the same method works. I'll show it to you. So, same method. So, and here is the picture. So, if this is your point P, the tangent space is, this is a line perpendicular to the direction, perpendicular to OP, that is the tangent space. Okay. So, now let us look at S2. How much time is left? Okay. Half an hour. Okay. It's very good you kept 90 minutes. Otherwise, in 15 minutes we can't do anything, right? Okay. So, so this is my example. ये कौन सा example? Did I give any number to the examples? Anyway, it doesn't matter. In the notes there are. By the way, but the notes are in some different order because I did not know your background, so they are more or less a summary of what we are doing here. Okay. So, compute Tp of S2. S2 is a set of all points such that I am taking a unit sphere. Okay. So, this is how the picture looks like. So, this is the north pole and this is the south pole. Okay. So, what should be the what is this? This is the tangent space at the south pole. Now, how do we know that every tangent space will be like this? Because I I can rotate and I can move this point to any point on the sphere, right? But we have not developed the machinery for this, so we have to do it by equations. Okay. So when we do SO3 and so on, you will see that this is obvious, right? No, it's obvious here. I mean, you can move along this great circle, right? And then this will be moved to a tangent plane on that great circle. Then you can go. What are these curves called? Meridian. You move in the other direction. So this means if you use these spherical coordinates, you can see that the dimension of the tangent space is always 2. Okay. So let's do it by equations. So take a point P equal to ABC on the sphere. Okay. So take a curve C from minus epsilon epsilon to the sphere with C of 0 equal to P, and CT is XT, YT and ZT. Okay. So what is these, because it has to be a curve inside the sphere, the x, y, z are not arbitrary. They have to satisfy a relation. What's the relation? XT square plus YT square plus ZT square is equal to 1. Okay. So differentiate this, what do you get? You get 2 times xt x prime t plus 2 y of t y prime t plus 2 and on the right side you will get 0. Now plug in t equal to 0. So for t is equal to 0, you get 2a x prime 0 plus 2c so this means now we can use a little bit of notation. These were the components of C prime at 0. And do you see anything familiar? The dot product, right? When are two vectors perpendicular, the dot product 0? When they are perpendicular. So this means ABC dot dot x prime 0 dot c prime t dot c prime 0 is equal to 0, right? So this means TPS2 is a subspace of all vectors u v w such that AU plus is this a subspace? When you add two such, you will get again. So, and now what is, how can I conclude that its dimension is 2? It's geometrically it's obvious. All vectors perpendicular to a vector form a, right? But here, because for example, let's say not all A, B and C can be 0. So, I can divide by A and I get U in terms of V and W, and that is what Dr. Vakas was saying. So, you have 2 degrees of freedom, so it will be a 2-dimensional space. So, it is a subspace of a, and why is it exactly 2 dimension? The same trick. If A square plus B square plus C square is equal to 1, let us suppose A is positive, then you can solve for A in terms of B and C, and then you vary B a little bit, keep other fixed, you will get one curve. You vary C a little bit and keep the other fixed, you will get another curve, and they will have non-zero tangents. So same arguing as in for S1, you see that using A square plus B square plus C square is equal to 1, and not all A, B, C can be 0. We see that
अच्छा साहब आपने ऑर्थोगोनैलिटी का तस्करा लास्ट टाइम नहीं किया वो लास्ट टाइम भी तो यू टेक द प्रोडक्ट एंड इट गिव्स यू 0 यू नो सो वहाँ पे भी
कहाँ पर जी उसमें नहीं मैंने किया था जी उसमें नहीं मैंने किया था बट
सेम होल्ड्स ट्रू
same holds true exactly so you see that dimension of and what do you get dimension of the n sphere, tangent space of the n sphere would be n, exactly 100% the same calculation. The advantage is that we are just working with equations, we do not have to know any special parameterization. Okay, now comes a interesting thing. Let's take, let set of all x y such that x y is equal to 0. So, what kind of set is this? Come on guys. G. Yeah, if x y is 0, one of x or y has to be 0. When x is 0, you are on the y axis. When y is 0, you are on the x axis. So this is, so z is, so z is union of x and y axis. Okay, so so what are the tangent spaces? No, not yet. Two points of z. Okay, so this is your, if I take a point here, now I am not going to, you can do it yourself. What is the dimension of the tangent space? 1, right? And if I take a point Q here, what is the dimension of the tangent space? 1, right? But if I take the origin, here is one direction and here is another direction. And when I look at the linear span, what is that? Because it has to be a vector space. I said, I made a distinction. I said that you take a curve passing through a point and look at its tangent, and the space generated by all such vectors is called the tangent space. So here, this is at the origin, the dimension of the tangent space is 2, right? And in geometry, we say this is a singular point, because except for this point, every other point has dimension 1. So away from this, this looks like a manifold of dimension 1, but here something is wrong. It's not even a manifold of dimension 2, but it's a singular point, right? So, here.
So another way of saying this is that at the origin, this manifold is not differentiable.
This is not a differentiable.
So therefore, and that's why one should not call it a manifold.
No.
Now I understand what you were saying.
Yeah, it's an algebraic curve.
It's
And algebraic curve means defined by polynomial equation.
Yeah. So it's a manifold to the right, manifold up and down, but not at one single one single point. So you can call it M everywhere except one point.
Exactly. For all points not on for all points except the origin, dimension of, so for all points P, dimension of is equal to 1, but dimension of T0 Z is equal to 2. It does not mean that at 0 it's some two-dimensional surface. No, by my definition, you look at all the tangent vectors and you look at the linear span of these. So the linear span of these is of course all of R2. Okay. Okay. Now let's take a more interesting.
सर
जी,
अगर यही चीज़ हम 3 डायमेंशंस में देखेंगे तो फिर उस केस में क्या हम ये कहेंगे कि टेंजेंट स्पेस की एट दैट ओरिजिन हमारे पास डायमेंशन 3 है?
वहाँ पे बिल्कुल आप तो आपका z क्या होगा?
एक्स वाई जी
इक्वल टू 0, राइट?
यस.
ठीक है. So at any point other than the origin, it will be one dimensional.
Yes sir.
But at origin something happens. Okay. नहीं वो उसमें this is also contained. So again you have to be a little bit careful. Okay.
Spanning में people talk about completeness also. So when you talk
No,
about,
but this is not a Hilbert space.
no, even if you talk about Rn, not about a Hilbert space, just so at 0 you come up with something which is a singularity that you say.
Yeah.
So it is not defined at that point.
It depends on.
But it is giving you a dimensionality which you are not getting at other points.
Yeah.
And one more question:
Can we finish it then? So because otherwise there's a very interesting example I wanted to make. So example. So we take a circle. Oh, it's not anyway. Okay, and we take this line. So our z is circle and tangent at a point. Let's give it some name. Now what is the dimension of the tangent spaces at every point. At all these points it is 1, right? But here also it is 1, right? Because this was just tangent to the tangent vector. So here also it is 1. But we feel that there is something special about n, about this point. Okay? And to see this, so I want you to imagine something. So let me draw it again. So suppose I remove one point here. I remove this. Then how many connected pieces means you can go from any point to any other point. How many pieces are left? You can go from here everywhere, and then you can join this and then travel here or travel here. So when you remove one point, you get a connected piece. Okay. Now what happens if you remove this? How many connected pieces are left? One is this portion, another is this portion, and another is, so you have 3 connected components. So this point behaves differently from every other point, and we say it's a singular point. Okay. So not tangent space normally detects the singularities, but when you have multiple points, you have to give some topological kind of argument. This is what we call a topology. Okay. हाँ? जब इस पॉइंट को रिमूव करेंगे, हाँ, सिंगुलरिटी, हाँ, जब तो वो, हाँ जी, बताइए क्या आपका सवाल है?
इस सिंगुलरिटी को अगर हम ऐड करें तो फिर ये सारा जो स्पेस बनेगा ये तो फिर वेक्टर स्पेस नहीं होगा ना?
ऑफ कोर्स वेक्टर स्पेस तो सर्कल भी नहीं है. So there is some serious problem. We have to discuss it. What is the issue? नहीं, इनसे मैं पूछूं.
सर ये जो आपने सिंगुलरिटी लगाई तो इस पे तो टेंजेंट स्पेस एग्जिस्ट नहीं करेगा ना? टेंजेंट स्पेस को हमने एक वेक्टर स्पेस का नाम दिया था.
Tangent space, if I give you any subset of the real numbers of Rn, of plane space, tangent space will always exist. Okay. But given a space, if the dimension of the tangent space at every other point is some integer n and it becomes lower or bigger at some point, then you say that is a singular point.
Maybe I can add in something over
please.
here to remove the confusion. If you are at a point P, then there is a tangent space there. If you are at another point Q, there is a tangent space there of vectors, but you cannot add this vector to that vector.
You cannot add tangent vectors from different spaces. You cannot.
From different points.
Tangent spaces at different points, the concept of adding to is not defined.
Yeah, that will bring us to parallel transport, and but that's not what he is talking about over here.
If we have a tangent space and there is a singular, if we have a space and there is a singularity in it, can we call it a tangent space?
What do you mean there's a singularity? There is a point P. At that point P, there is a tangent space. Here what you see is a one-dimensional tangent space to the right, one-dimensional tangent space up. At the point 0, there is a tangent space, but
you're talking about this example?
Yeah.
Okay.
At that point, it is a two-dimensional tangent space.
Yeah, because it is spanned by linear span of this direction and this direction.
That's correct.
So
now you can add together vectors in the two-dimensional tangent space, and they will remain always within that space, and similarly for the one dimension and the one dimensional there. But you cannot add vectors from two different spaces.
You cannot add vectors from two different spaces. Okay. For example, you can, if I give you a circle, even more. If I give you the sphere, and I give you another. Does it make sense to add these vectors to these vectors? Doesn't make, right? So the tangent space is only, you can add vectors in the same, vectors which are issuing from the same point, right? That you can do, but not from, that you can do it, but that's another notion which maybe Parvez will discuss, okay? So, do we have time or? Okay, good. Okay. So,
Excuse me, sir. I have a question, sir. Sir, if we are removing the end point, then how is these line segments on the left and right side of the point connected to the rest of the circle?
sorry, what did you say?
Sir,
If I remove?
sir, end point over with horizontal tangent. Point with the horizontal tangent on top. Yes, sir.
If I remove this,
Yes, sir. So,
if I remove this, then okay, at this point is retained, right?
yes, sir.
So, one component you can,
Oh,
another component, and the third is,
this. So we are considering them separately as connected. They are
it
considered
has
separate.
disconnected and it has three connected components,
Oh,
right?
oh.
Whereas when I remove any other point like this, it is only, it stays connected, right? You can go from any point in the except this point to any other point, okay?
सर हाउस डोर स्पेस जो है उसका आप इसके साथ लिंक
क्या कह रहे हैं?
हाउस डोर स्पेस
House of space.
House of space, हाँ क्या? These are all house of spaces. Why?
because it is disconnected.
Come on, because it is a subset of R2. R2. What is Hausdorff?
When we take the intersection of two subspace, it will
No.
give null set.
Hausdorff means you can surround 2 points by small discs or rectangles, so which do not intersect.
Yes, sir. Intersection is 0.
You have to, please try to be precise in your thinking also, right? It's a very bad joke, but somebody said housed off means housed off. Matlab, one can be put in a small house and another can be put in a small house, and they do not. This is the meaning of housed off.
Yes,
Okay?
sir. Yes.
Now, so I'm coming to this. It's good that you brought. So now I'll end this lecture with some topological notions. Okay. So. So, concept of concepts of topology. So an open set O of Rn is a set such that if P is an O, there is a box rectangular box so let's give P some coordinates a1 up to an. A1 minus epsilon, A1 plus epsilon cross okay. So let me show you this picture. What would be a small rectangular box in 2D? Here's your point P. You can go in this direction or you can go in this direction and complete it. But of course you do not keep the, let me draw it again, P, so you can go in this. Okay, so this is your box, right? Rectangular box in 2D, and this is in ND. So this is the meaning of an open set. Okay, that with every point it has a small rectangle that lies entirely. It's the same like what's an open interval? You see the difference between open and closed interval, right? When you look at the boundary point, there is no small interval which lies inside the rectangle, right? So that's a difference. Okay, and we say that we say that a subset U of Z is open if for every point P of U there is an open set O in Rn such that I'll make, we say that a subset U of Z is open if there is an open set O in Rn such that Z such that U is equal to O intersection Z. Okay, so you take the open sets of the ambient space and you intersect them with your set Z, then you will get the open sets of the of your set Z which you started with. Okay.
Of course, all these epsilons don't have to be equal.
No, they don't have to be, but you can always take them to be equal, right? By choosing the minimal one of them. Okay, and then
Process I'm learning is these have to do with the dimensionality, like xy will give me a rectangle.
oh, sure. Cross means this. If I take S any set and T any set, S cross T by definition is set of all xy such that X is in S and y is in. This is the definition. So if I take the interval I, open interval 1 1, so I cross I, this is set of all x y such that 1 is less than x is less than 1 2 sorry 1 is less than x is less than 2, and I cross I cross I, this is set of all x y z such that x is between 1 and 2, y is between 1 and 2, and z is between 1 and. Is it clear or okay? So then throughout this course we will be needing the notion of a differentiable function. So what's a differentiable function? If locally it's the restriction of a differentiable function in the ambient space. So let me define it formally. So differentiable functions on subsets Z of Rn. So definition, take P in Z, a function f defined in a neighborhood Z intersection O open in Rn is differentiable at P if there is a differentiable function capital F from O to R. You know, when we are in Euclidean space, and it's clear that all the components, the function, this f of x1 up to xn, it should be a differentiable function of each of the variables and should have continuous partial, the usual definition of advanced calculus. So if there is a differentiable function f from O to R such that f restricted to O intersection Z is equal to f. Okay. So this is called a function differentiable at a point. And when would be a function differentiable on all of Z? If it is differentiable at every point. Okay. So basically these are restrictions of differentiable functions in the ambient space. Okay. So I think this is all I had to say, and next time we will start with integral curves. That's the heart of the subject.
Sir, why we need open set to define topology?
That's the definition of topology, because why do we need open
Sir,
sets?
what will be the problem if we
Because
if we are
look, it took mathematicians
lost.
centuries to reach this point. Without that, you cannot define continuity, right? Because what was it? We say function is, I mean, intuitively continuous if it is, if I take a value f of p, then when x is near p, f of p is near. If I take 2 points p and q, the function f is continuous if the values, if I take p near q, f of p should be approximately f of q. But what is the meaning of this approximately? Right?
Yes.
That's why people invented this concept. But I encourage you to think intuitively. That is that's the creative stage of mathematics. In the creative stage, you don't care about logic at all. Okay, and it took mathematicians maybe how many years after Newton and Weierstrass and so on, maybe 200 years till they came up with this.
Okay, sir.
Okay. So, what's your background in calculus? What have you done? Maybe I'm assuming too much. Do you know differentiable functions of two variables? Yes? We don't care too much about rigor. Okay? We just want you to know. So give me an example of a differentiable function in two variables. Just one person. Yes? Fxy equal to xy. Yes. So all polynomials are differentiable functions. All signs, usual functions of polynomials, sine of x plus y, sine of x square plus y square, e to the x times e to the y, all the usual functions. In fact, any convergent power series in x and y, that is a differentiable function. Okay. So any function which can be represented as a power series locally is a, and this is the famous Taylor and Maclaurin series. Okay. जी